All right, welcome, Math 13 students. I'm going to continue my review of the exam 3 material tonight. Tonight, I'm going to focus on examples, the kind of questions I could ask you to do on exam number 3. And I'll take them essentially section by section, chapter by chapter. And I'll begin with chapter in section 7.1. Confidence intervals for population proportions. Given a confidence interval, I will remind you that it is built by taking the point estimate p hat, that's that x over n, and adding and subtracting the margin of error, e. And I'll put a formula for that up in a moment. It's really not where I want to go just yet. So given that that is that's the way the confidence interval is put together, if I give you a confidence interval for a population proportion, for example, 0.46 less than p less than 0.64, I can ask you to do two distinctly different things. So there's my given confidence interval. I can ask you to find both the point estimate and the margin of error. That margin of error is the E right up there. The point estimate is the P hat. So let me run through that example. So you're given a confidence interval. You're really not given any detail as to where the confidence interval came from, only that this is the confidence interval. And it's important to remember that this exists on a number line. So there's my confidence interval, and the way it is built, the point estimate p hat is right there in the middle. We add the margin of error and we subtract the margin of error to get these guys here. So to find the point estimate, the p hat, that's exactly halfway between those two values. If I jump over to my calculator quickly, I can emphasize some order of operation issues. So I take care of the numerator first, add those together, and then divide that result by 2. So 0.55, that's my point estimate, 0.55. So let me stop my sharing. So now that I've got the 0.55 right here in the center, it's relatively easy to figure out the margin of error. So that margin of error means I'll start with the 0.64. I need this distance in here, so I'll subtract the 0.55. So 0.64 minus 0.55 is 0.09, and there is my margin of error. So I've got to be given the margin of error. Then I can go ahead and find, given the two endpoints, I can find my point estimate, p hat, and then I can use that endpoint there. And now I've got 2 points to work with, and I can find my margin of error, E. At the end of the day, I can choose perhaps to rewrite my confidence interval as p hat plus or minus my margin of error. So we would have 0.55 plus or minus 0.09. And you'd realize pretty quickly that if you actually did the arithmetic for this guy right here, adding and subtracting the 0.09, you get right back to these guys right there. So at a very basic level, if I give you a confidence interval, you should be able to pick out either the point estimate or the margin of error, if that is what is required. I can also ask you to do a couple of things with the actual confidence interval. Now that confidence interval, that's that p hat plus or minus the margin of error. That margin of error z alpha over 2 p hat q hat and n. It is conceivable that if I give you data, say x is equal to 46, n is equal to 100, and we're working with a 95% confidence interval, I can ask students to find the margin of error E. And to do that, I've got to remember a couple of things. At the most basic level, I've got to remember how to calculate p hat and q hat from my sample. That's not hard to do. Then I also need to be able to calculate my critical value or values. So p hat 46 over 100, 0.46. Q hat 1 minus p hat 1 minus 0.46 equals 0.54. We already know what n is. Remember, p hat and q hat must always add to 1. The z alpha over 2 comes to us from the inverse norm tool on the calculator. And I'm going to go ahead and switch to a fresh sheet, and then I'll take care of this. So anytime I need a critical value, that's where I'll use the inverse normal program. So if we're building a 95% confidence interval, the alpha is 5%. That's the chance of making an error with the interval, getting an interval that doesn't contain the object we're trying to estimate. So it's the z distribution, 0 in the middle. I got two critical values, one on either side. The area, 0.05 over 2. It also means the area in the middle is 95% of the area in the graph. So let me jump back over to my calculator. And second to distributions. There's my inverse normal. The area I am interested in is 0.05 divided by 2. That's just the area in one of the tails. And I'm going to use the left-hand tail because some students may not have access to this version. I'll go ahead and paste that in, and I'll get negative, and I like 3 decimal places, 960, or negative 1.96 to 3 decimal places, because the fourth one out here is a 9. So this third one's a 0, and this becomes a 6. So the critical value over here, negative 1.96. The value over here, positive 1.96. You'll remember the plus minus in the formula for the confidence interval. That's where it comes from. I only need the positive one. So I've got this value here for my z alpha over 2. So my margin of error here is 1.96 times 0.46, 0.54, all over 100. That's in the square root there. That's my margin of error. And there we go. This one's a very easy calculation to do. We are really treated kindly by the order of operations. 0.46 times 0.54 divided by 100. Goes in just like butter. And I get a 0.0976. There's no real hard and fast rounding rule here. I'll take 1 decimal place, excuse me, 2 decimal places, 0.10 if I take 2 decimal places here, the 6 if I take 2 decimal places here, the 7 means the 9 becomes a 10. So margin of error, 0.10.
Can you say that last part again, please, about the rounding?
Let me bring that screen back. There's no hard and fast rounding rule. I'll just ask you to round to some decimal place. I'll take 2 decimal places in this example. So if I look at the second decimal place, I see the 9. If I want 2, I have to look at the third. The third is a 7, so that's 5 or larger. That means this 9 has to be rounded up. And when I round the 9 up, it becomes essentially a 10. So this 0 becomes a 1, and that 9 turns into a 0.
All right, thank you.
Yeah. So there's my margin of error. Now, the other thing I can ask you to do is given data, I can ask you to construct a confidence interval for a proportion. So for the sake of argument, let's let x equal 46 again. Let's let n equal 100, and we're going to construct the 90% confidence interval. Now, I already know what my point estimate is. And I always ask students on this type of question, what's the point estimate? Because that's your starting point. It's also important to remember that when it comes to building or constructing the confidence interval here, when I want to construct this confidence interval, I really don't want to use the formula at all. It's the 1 prop z interval. 1 prop z interval. So let me switch back over here and switch my screen. And that lives under stat. And by the way, I believe all the keystrokes, excuse me. I believe all the keystrokes are laid out pretty clearly before the problem set in the respective sections. So I scroll on down, I find my 1 prop z interval. It has a place for my x, 46, a place for my n of 100, confidence level 0.90. I said 0.90. 90%. Now I'll just hit calculate. And there we go. Here again, there's no real rounding error, or excuse me, there's no real rounding rule. I usually just ask students for 2 to 3 decimal places. That last one was 2. I'll take this one to 3. By the way, here's my point estimate. See the little hat on the P? So 0.378, 0.541, but this is a 9, so 542. This is a 0, so the 8 stays 8. 0.378. Less than P, less than 0. What did I say? 542. So when it comes to constructing a confidence interval, it is the one prop Z interval. This is really the tool that we would use. It's the one we like. It works very, very well. All right, so at that point, we've got now almost everything from this section out of the way. There's one last question I might ask you. I might ask you to determine sample size. So we need to be given a couple of details. We need a level of confidence. And we need a target margin of error. And we have two distinctly different formulas. We have n equals z alpha over 2 squared times the 0.25 divided by e squared, or z alpha over 2 squared times p times q all over e squared. We use this one if we have no provided detail on P and Q. We use this one if the problem does contain detail on P and Q. But you've got to be given the margin of error and the level of confidence. The level of confidence helps us get the Z alpha over 2. The margin of error gives us our denominator. Those have to be provided. If we know nothing about P and Q, we assume 0.25. You can see in our notes why we do that. So the questions will look like: find the sample size needed. And that's always a clue because it says find the sample size needed to be 90% confident we are within 3% of the true proportion. And there is, for the first example, there is no detail on P and Q. And then the second example, we're going to assume previous research has shown that P is equal to 0.31 and Q is equal to 0.69. But that's got to be provided. So we want to build a 90% confidence level once we're done here. And we want to be within 3% of the true proportion. So that 90% confidence level, that will get me my Z alpha over 2. The level of confidence is 3%. So this gets me the chance to go over inverse norm one more time. I draw these pictures so much, I just tend to draw them in a very abstract fashion. So there's my Z distribution. I got 2 critical values. Let me jump over to my calculator. There we go. Let's see, if we have a 90% confidence interval, so we got 0.90 And that's what we have in the center. 10% split between the two tails. So I'll set it up this way this time. And plus or minus 1.645. Plus or minus 1.6448. So the 8 makes this a 5. All right. That's my Z alpha over 2. And I'm now ready to go ahead. Oh, not E. We want N. 1.645 squared times 0.25 divided by a 0.03. Remember, E was 3%, which is 0.03, and don't forget to square. Again, the order of operations really does play nice with everything we need to do here. So I have 1.645 squared times 0.25. Oh, hold on, that's not what I want. 1.645 squared times 0.25 divided by 0.03 and square him. Order of operations tells us to do exponents before any addition, multiplication, or division, which is why the order of operations is so pliable. So 751.67. We always round our N up, so 752. If we round down for whatever reason, you got to remember this is a floor. We can't go below that number. And since we'll need whole numbers, it always indicates we round up. Now, for the second example, we had a P and a Q provided by previous research. So N is equal to 1.645 squared times 0.31 times 0.69, 0.03 squared. So you can see it's a very similar calculation. And again, the order of operations is just fine. We'll take care of all the numerator and then divide. We're ready to go. All right, so I got the detail about the internet. By the way, if it does give you issue and you're in the middle of your exam, do reach out and we can try to work with that. So don't let that reach out if there's an issue. So 1.645 squared times 0.31 times 0.69 divided by 0.03. And we got a square in there. We'll hit enter. See this one here, it seems like we should be rounded down, but no, 0. Anything. Point anything means this guy goes up. So 644. That number here is a floor. You're not supposed to go below. So those are honestly, the sample size problems here are truly the ones my students struggle with the most out of chapter 7. You guys really honestly do pretty good with the one prop confidence interval. 7.2, after we get 7.1 out of the way, goes quite a bit easier. So this is confidence intervals for a mean. We have the point estimate. X bar. We have a margin of error. But since we're estimating a mean, it's a different formula. We use the t-distribution s over the square root of n. There's some similarity in structure to the previous section. I usually don't ask students to find the margin of error directly here. But again, if I give you a confidence interval, you should be able to find both the point estimate and the margin of error using those techniques from 7.1. To build a confidence interval, we use t interval. And it works quite well. We can use it with summary statistics or actual sample data. You see me do examples with both. I'm going to do the summary stat example. So this time we're going to build the 99% confidence interval for vehicle speed. So we're looking at a bunch of cars. We have 69.1 miles per hour is the average. The standard deviation is 7.3 miles per hour, and my sample size is 100. So I'm going to go ahead and build that confidence interval. Don't pick up the z interval by mistake. I'll do it correctly, then I'll show you how to not make the mistake of picking up the wrong tool. So I have statistics. My mean was 69.1 miles per hour. 7.3 was the standard deviation, and 100 was the sample size. We're constructing the 99% confidence interval. We're going to go ahead and calculate that. And there we go. My sample statistics have one decimal place, so I'll take one decimal place here. 67.2 because of the 8. 71.0 because of the 1.
Can you do it again? I'm sorry. On the
One
calculator.
moment here, hold on. I didn't quite get that. So what was the question?
I said, can you do it on the calculator again? My internet's
I
kind of
can.
laggy. So
Okay. And by the way, these keystrokes are in your text right below, right before the problem set. And they're also in God knows where else, a whole bunch of other places. So, so don't get freaked out if it doesn't work during the quizzes or exams. Remember, you've got lots of places to look. So, t interval, enter. I have stats. So I've entered the 69.1, the 7.3, and the 100 for the mean, the standard deviation, and the sample size. The confidence level, remember, it often comes in percent, but you've got to change it to a decimal. And then just click enter, and there we go. And it spits back the stuff you put in, if you will. So you can sometimes see if you've, maybe made a simple typo, 7.4 instead of 7.3, maybe. I don't know. Anyway, did that help?
yes, thank you.
Yeah, the keystrokes, once you get them down, they're really not that particularly bad for this particular process. So I ask no sample size question, but I do ask people for the requirements. The requirements, they're very simple. We need a simple random sample. and then either or, one, the other, or both. You don't need them both, just one or the other. You need either an n greater than 30 and or a population that has an approximately normal distribution. The only time this one really comes into play is when your sample size doesn't hit this mark and n is less than or equal to 30. If you've got a small sample, you really need a normally distributed population before the results are reliable. Your calculator doesn't know the difference, but it should be there in the problem somewhere. And that's chapter 7. Now let's see, what time is it? All right, so let's start chapter 8. I'll probably want to finish up chapter 8, then deal with chapter 10 tomorrow. The exam is available through 8 p.m. tomorrow night. It says due today, but everyone gets an extra day without worry. All right, so chapter 8 was all about hypothesis testing. Now, I ran through the details yesterday, and I'm not going to run through the actual details today. As I said, I want to run through some examples. Part of the issue that students face with the chapter 8 material is the fact that 8.1 is so dense and heavy in detail. All of the detail honestly gets repeated at appropriate times as one goes through the balance of the semester, but it can be super overwhelming to try to take it all in 8.1. 8.1 really just shows you all the little bits and pieces, all of them. Whereas 8.2 and 8.3 actually go about the business of conducting a test of hypothesis. Using all the little bits and pieces developed in 8.1. But 8.2 and 8.3 are really handled via your calculator. So as I say, it can be a little confusing. So there's a couple of things that I need to have you know and be able to do from 8.1. You need to be able to write the null and the alternative hypothesis. Phrases like at least, at most, less than, more than, all have a role to play. All have a role to play in determining where things fall on the two hypotheses. I will remind people that when we write the null hypothesis, it's always written with an equal sign. The alternative hypothesis is always written with a strict inequality, a less than, a greater than, or a not equal to. So that's the first thing I need to have you be able to do. In terms of basic detail, and a lot of this, as I say, gets covered a couple of times in 8.1 and 8.2. Finding a test statistic. For claims for a proportion, the test statistic is z equals p hat minus p, and then downstairs we'll have p and q all over n in the square root. P hat and n come to us from our sample, p and q come to us from the null hypothesis. For a mean, we use the t-distribution, and it's x bar minus mu divided by s over the square root of n. This one is a little bit more tricky in terms of the order of operations. This one here, after you calculate your numerator, you still need parentheses around the denominator. Let me give you an example of finding the test statistic for a proportion. Claim. The proportion is more than 54%. That's the population proportion. Maybe I should have put the word population in there. Is more than 54%. We have x equals 57 and n equals 100. So as I say, this is the kind of detail we need to be able to work with. So more than 54%. That translates as P is greater than 54%. So that means I've got my alternative hypothesis, my null hypothesis, P equals 54%. The alternative, P is greater than 54%, although I really only need this guy here. So once I've got that, that also tells me I've got Q, 46%. P and Q have got to add up to 1. I've also got my P hat, 57 over 100, or 0.57. So I've got everything I need for that calculation. My test statistic is P hat 0.57 minus 0.54 divided 0.54, 0.46 divided by 100, and that's all within the square root. So that's my test statistic. The order of operations plays fairly nice with us as long as we remember to take care of the numerator material first. So 0.57 minus 0.54. We're going to divide that by, I can pick up my square root, and then 0.54 times 0.46 divided by 100. There we go. So 0.602. Again, no hard and fast rounding rule. So that would be my test statistic, and then I could plot that or use it to calculate a p-value. The p-value. Confusing because it's capital P, and there's a lot of P around right now. And this is the probability of getting a value at least as extreme as the test statistic. Students understand this other thing much better. The p-value, we compare it to alpha. That's that level of significance. Common values of alpha, 1%, 5%, 10%. We've already encountered alpha back in the confidence interval notions. We really start to use it here. And if the p is less than or equal to the alpha, if that's the case, we will go ahead and reject the null hypothesis. If p is greater than alpha, we fail to reject the null hypothesis. And if that's a little bit confusing, when I get into the material in 8.2, I'm going to remind students again about how we like to deal with the outcome of our tests. So I can do a couple of different things with this p-value here. if P equals 0.0471, will H naught be rejected if alpha is equal to 5%? Yes or no? Or does it depend? Or maybe we need more information. I need to compare my p-value and my alpha. Which one is bigger? The alpha is bigger, so we will reject the null hypothesis. And I do that because, once again, my p-value is less than or equal to my alpha. So I reject the null hypothesis. Same issue. We're going to change things around and we're going to say, well, all right, blah, blah, blah. Suppose we change things around and suppose now alpha is 1%. 1%. So now 0.0471, 0.01. In this case, because we've changed the level of significance, which, by the way, we are entitled to do because the researcher is the person that decides this. It's not a math question. So now we will fail to reject the null hypothesis. The jury has come back with a not guilty verdict. And all of that is because my p-value was larger than my alpha. The other thing I can ask you to do is to find the p-value. Given you need at least the alternative hypothesis and the test statistic. I can ask you to find the p-value. All right, so we have a claim about a proportion. We have H naught, P equals 37%, and H1, P is greater than 37%. I need the alternative hypothesis because I need to determine the test. So the test is what I'll need to know the type of test, left tail, right tail, or two tail. And I need my test statistic. 1.973. So if I've got these things, the test statistic and the tail of the test, I can then go ahead and find the p-value. Drawing my z distribution, there's the 0 in the middle. Here's my test statistic, 1.973. It is a right tail test, so I am interested in that area there. That area is the p-value, and in this case, that area is equal to something. What tool do we use to find that area? That's the normal CDF tool. So we use the normal CDF tool to find the probability for the area. They are synonymous. So let me go ahead, share my screen. Distributions, normal CDF. The lower bound in this case is 1.973. The upper bound is 10 raised to the 9th power. I go over these keystrokes any number of places in the Canvas core shell. There it is. And there's my area, 0.0242. It's a probability, so I want 3 significant digits. There is a rounding rule here. There's the third, the 4 means the 2 stays 2, 0.0242. All right, so 0.0242. That really pretty much brings me to the end of my review for 8.1. We're also just about out of time, so I will handle the 8.2, 8.3, and the chapter 10 material tomorrow. But I will remind students that they focus on hypothesis tests, and we'll run through the basics of a hypothesis test. And before I leave you tonight, I'm going to lay out the detail for a hypothesis test. And this is where we'll end. We will use exclusively the p-value approach, regardless of what it says on any problem on our homework. We do p-values. So we'll write the null and the alternative hypothesis. We'll want to identify the initial claim. That's the claim that's written. Sometimes it's null, sometimes it's the alternative. Step number 2 is to find the p-value. That's where we'll use our TI 84. Then I compare that with alpha. That's my rule there. Once I do that, I can determine the outcome of my test, reject or fail to reject. Then I can address the initial claim. Every test of hypothesis with the p-value approach follows this trajectory or recipe if you like to cook or bake. 1, 2, 3, 4, 5. Those 5 steps, I can ask you to reproduce any one of those 5 steps or several of those 5 steps within a given problem. The challenges students will face is making sure they have the correct hypotheses because they've got to address the initial claim, and they'll also need it here when they get to the TI-84. That will go ahead and get you your p-value, but you've got to use the right tool. You can then compare that with alpha to determine the outcome, reject or fail to reject. Then you can circle back around and pick up that initial claim. So that's where we're going to pick it up tomorrow. I'm going to stop my recording.
I have a question.
Sure.
So you know the discussions?
Oh, you're talking about the lab discussions.
Oh yeah, sorry.
Yes.
About the lab discussions, how would I go about turning those in?
You know what? Can I just research that for a day? I might actually open that one back up for you. That
Okay,
one
I think it was the so it was the, let me see.
the most
It
recent.
was the neuroplasticity.
Okay, well,
And
we'll take a
then
look
the grip.
and I'll take a look too. And I'll see what I can do. All right.
Yeah.
I have a question.
And then
too. Sorry, after you finished, Delilah.
Mhm.
oh sorry. So does the lab for statistics and the other class, because you know it's 2 like kind of separate courses.
Right.
Do they combine at the end of the semester?
No, they do not. The lab supports the regular course, the Math 13 course.
Okay.
And what a student really wants to do is to make sure they pass the Math 13 with a grade of C or better.
Yes.
That's the real goal, honestly. And what happens in the lab if you pass the Math 13 really doesn't matter. You either get a pass or a no pass, but you don't have to come back and retake the lab or anything like that. It's really the Math 13 that's the
Okay. Is there gonna be any like extra credit for the statistics?
yes.
Not the lab, the other one.
Yes, there, in fact, there is, on the exam, there's some extra credit. And I'm going to make, one of the quizzes, the very last quiz is going to be extra credit also.
Okay.
And there's probably going to be one or two other things in there also. But I believe that's what's going to happen.
Okay then. Thank you.
Naomi?
All right, my question is, so on Canvas, the exam is due tonight